Here we go. There you go. What's that? Octane. I will take it. So we're going to do this octane. And then, what are my substituents? Yeah, so it's going to be ethyl first, then methyl, then we're going to squeeze propyl in here. Right, am I going to number blue or orange? It's going to be blue. So the reason here, and this is going to come up here in a little bit again, is when I go blue, right? Oh, sorry, blue, let me go to 5. Right, I get 4, 5. When I go orange, I get 1, 2, 3, 4, 5. Right? But my first number when I go blue in my name is 4. And then the second number is also 4. So 4, 4 is better than 4, 5. So we're going to go blue. So we're going to get 4-methyl, 4-propyl, 5-ethyl. So we've got like 2 more rules to go through for IUPAC naming, and then for basic straight chain hydrocarbons, and then we're going to go on to rings. I already got this next slide queued up. Look at that. So the rule number 6 is if you have a compound that has 2 same longest chains, you pick the longest chain to be your parent hydrocarbon that has the most substituents. That just makes it way easier to name that molecule, because when you pick the chain that has the most substituents, you get the simplest substituent names to use, and it'll just make your life easier. So what do I mean? Let's click over. Doop, 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 doop. Right? So let's say I have this. There are multiple different hexanes in this molecule, but I'm just going to pick like a couple here. So there's this hexane. How many substituents are coming off of that hexane? 4. So I got 4 substituents of that one. If I pick this hexane, 1, 2, 3, 4, 5, 6, I get 3, right? If I pick this hexane, I get 2. So I'm going to pick the hexane that has the most substituents coming off of it, because that's going to give me the simplest substituents, the ones that are easiest to name. So I'm going to redraw this so you can actually see what the heck's going on. It's going to be a little crappy looking, but whatever. So it's going to be hexane. Right, this is going to be our, we'll go with green again. This is going to be our 1, 2, 3, 4, 5, 6, our hexane. So what are my substituents? Dimethyl. So I have dimethyl. So we've got a methyl right here and right here. And what is my other substituent? Diethyl. Yep. I almost gave myself enough space to actually do this. All right. So in this case, my molecule is symmetrical. So it doesn't matter which way I number. So I'm going to just number this way. So I'm going to have a group at 2, 3, 4, and 5. So I'm going to be 2,5-dimethyl and 3,4-diethyl. So 3,4-diethyl, 2,5-dimethyl hexane. So you're always going to try to pick the chain that has the most branches. It just makes your life way, way easier. All right, so what's my longest chain for this one? It is octane. And the octane we're going to pick is that octane there. So we're going to be octane. And then what are my substituents? We got trimethyl. It kind of goes in the middle this time. I have a propyl and I have an ethyl. We did it, and these almost look like letters. This is great. So am I going to number blue, or am I going to number orange? So if I go blue, I get 2. Oh, I should probably use blue as a color. I get 2, 3, and then my next substituent is 5. Right? If I go orange, I get 2, 3, 4. So 2 and 2 are tied, 3 and 3 are tied. My next substituent gets the number 4 if I go orange, which is less than 5. So I'm going to want to go in the orange direction to number my molecule. So we're going to be 4 propyl. We're going to be 2, 3, 7. And we're going to pretend that fits in there. We're going to be 6 ethyl. No big deal. Super easy. Barely any inconvenience. All right, cool. You gotta make something you can actually name. It's important. There we go. You should be able to name that. Cool. All right. So what's my longest chain? I think it's octane again. Everyone on board with this one?
The question was, why was this student counting heptane? And the answer is surprising.
Maybe because I can't count, we'll find out. 1, 2, 3, 4, 5, 6, 7. Because you're smarter than me. How does that feel? I can make you the host of this Zoom, no problem. I can just sit back. Like, wheels are falling off. Okay. Yeah. Sure, go ahead.
So the question here was, why didn't we use the horizontal heptane as our parent hydrocarbon?
Is if you go straight across, like the whole point of what we're doing is we're trying to find the chain that has the most substituents on it. So the heptane that I pointed out has 1, 2, 3, 4, 5 substituents. If you just went straight across, you would have 1, 2, 3, 4 substituents. So just find the one that has the most substituents. So this is going to be heptane. And then substituents on this. Got ethyl, methyl, how many methyls? Dimethyl. Triethyl. Okay, we're gonna. So, do I want to number blue, or do I want to number orange? Or do I care? I don't think I care. Yeah, either way is the same. It's symmetrical. So we could go 2, 3, 4, 5, 6. So we're going to have 3, 4, 5 trimethyl. We're going to have 2, 6 dimethylheptane. Hokey dokey? Seem pretty easy? Now, we just went through all of this. I'm going to go back to this slide I had. Rule 7 lets us cheat on Rule 6. So Rule 7 lets us use things like isopropyl, sec-butyl, which I have to show you in a second, and tert-butyl as substituent names, even though they're not 100% IUPAC approved. The IUPAC way of naming things gets really complicated really fast in terms of we start putting things with like parentheses and brackets and stuff, and I don't ever expect you to be able to name like that. So isopropyl, sec-butyl, tert-butyl let us kind of use bigger substituents, or to be able to name bigger substituents so we don't have to do all the nitty-gritty naming. So let's look at, I have a good one here. I'm going to redo this one right here. But I'm going to use isopropyl to name it. So I think it looks something like this. Right? So if I say this is my longest chain, that's a hexane again, right? But it doesn't have the most substituents. But what I'm getting to do now is I'm getting to say that this and this it's a CH3 bonded to a CH bonded to a CH3. What's the name of that group? Really, those are two like horrific threes. So 3 carbons is propyl, but what is this shape? What is the prefix for this shape? That's CH iso. So this is isopropyl. So that's letting me cheat and say that this is going to be I don't know why I made it green. Isopropyl hexane. And then I just need the numbers, in this case 3, 4, diisopropyl hexane. So I can kind of cheat and not have to use the chain that has the most substituents if there are some regular structures that I know how to name. So like isopropyl, tert-butyl, and I'm going to show you sec-butyl in a second. So like you could have so the longest chain here is right here, right? Is heptane, right? So this would be tert-butyl heptane on carbon 4, right? Because this is called tert-butyl. So this is where we get to use those naming things that we, the names of the isomers that we had learned earlier. This is where we get to use those. So another one that I hadn't shown you is this right here, where you have 4 carbons, 1, 2, 3, 4. But you're bonded to the second carbon of the butyl. This is called sec-butyl. There's like one homework problem that uses sec-butyl, so I always make sure I show it. So this would be 1, 2, 3, 4, 5, 6, 7, 8. This would be like 4 sec-butyl octane. So this is letting us cheat on the use the chain that has the most substituents because we have these groups we know how to name. Most of the time, I'm going to kind of default to you using the IUPAC names. If we were like not in a pandemic and we had like actual tests that you wrote things on, I would take either. The homework is going to be pretty specific if it wants IUPAC or if it's going to allow you to use isopropyl, sec-butyl, and that kind of stuff. Or the naming there is going to be like pull-down menus. So, like, you'll just know what your options are. But this is just the way that, like, if you see isopropyl something or other, that you'll know what that structure is and kind of where to put it. So are we good on naming basic, like, hydrocarbons? That seem reasonable? No one's saying no. So I'm assuming we are good. So we're going to go on to cycloalkanes. All right. So these are just carbons that form a ring, right? The basic formula is just CN, where the N's the number of carbons, H2N, which makes sense because, like, if you look at this structure, every carbon in the ring is simply a CH2. Right, so it's just a bunch of CH2 stuck together. So this is C5H10. The naming at a base level is super easy, right? You add cyclo to the hydrocarbon name. So what I just showed you, right, has 5 carbons. So this is going to be cyclo because those carbons are arranged in a ring, and pentane because there are 5 carbons. This would be cyclo butane in a ring, 4 carbons. Now, some of you may have had a McPherson for Gen Chem, either AMAC or KMAC, and they may have told you about their youngest child. I was over their house once, and he was like 5 or 6, and he walks up to me, and he shows me this shape. He's like, "Do you know what this is?" And I was like, "Yeah, it's cyclohexane." And he looked at me like I was the dumbest adult he'd ever met in his entire life. He was like, "No," and just like turned around and walked away. Didn't even tell me what the right answer was. Just like, this old person's a lost cause. There's nothing for me here. So this is just cyclohexane. So I've lost shapes in my life now. They're all just molecules to me. All right. So that's the basics of naming rings. There are, I kind of call them extra rules, kind of guidelines. They kind of just steal from the other rules that we already have, but I just like to reiterate them. So 2, it's called additional rules for naming cycloalkanes. Right, so the first one, the cycloalkane is your parent hydrocarbon. Unless the alkyl chain attached to it has more carbons. Right, so we'll let you write that for a second, then I'll flip over to the next slide. So we have something like this, right? So we've got a cyclohexane, and then how many carbons do we have attached to it? 4. So that means that our cyclohexane gets to be the parent hydrocarbon, and then we just have butyl as a substituent. Now, when you only have one group on a ring, you don't have to put a number.
So I was asked here if you put a 1 in front of the substituent name if I'd count it wrong.
No. This is where I say, like, I have bigger fish to fry. But it's not needed. No number with only one group on the ring. It's not needed because since it's a ring, any carbon can be carbon number 1, right? It doesn't matter which carbon I put butyl on, I'm going to always get the exact same thing. So when you only have one group, you don't have to, the number is redundant. Now, if I have a situation like this, now the chain has 5 carbons, the ring has 4 carbons, so the chain is going to be the parent hydrocarbon here. And we do the exact same thing to make a ring a substituent that we would to make just a straight chain substituent. We remove A-N-E and add Y-L. So this will be cyclobutyl pentane. And this will be 3. 3 cyclobutyl pentane. So far, so good? Cool. All right, rule number 2. So this is definitely a ripoff. If there's more, if there is more than one substituent, list them in alphabetical order. Never forget. Right? The first substituent, right, is always 1. So there will always be, I should say, not the first. One substituent is always number 1. So you number to make the second substituent have the lowest number. So whenever you have a ring, you always start numbering at 1. And since that's the case, have to look at the next substituent to decide where you're going to start numbering. So I'm going to... Are we good here? My handwriting's trash. So, for example, let's go... Right, so here, this one's... I've got 2 substituents. So I'm going to be... What is this going to be? We won't worry about the numbers right now, but just what is everything going to be minus the numbers? Yep. Yep. Ethyl and methyl. So there's two ways I can number this. I can go 1, and then I can go 2, or I can go 1, and I can go 2. So here the numbers are exactly the same, so we fall back to the rules that we had before, which is, well, whatever comes first alphabetically, since it's a tie, everything's exactly the same, so this is going to be 1 ethyl, 2 methyl. So that one's pretty straightforward. So if we have something like this, and then this is where I start messing with you, where I start drawing like 7-membered rings and 9-membered rings just to make you draw them, because they're the most awkward things ever to draw. So this is going to be cycloheptane, right? And now there's a bunch of different places I can start and have my carbon be carbon number 1, right? The blue carbon could be carbon number 1, the orange carbon could be carbon number 1, or the yellow carbon could be carbon number 1. We can kind of eliminate the blue carbon right off the bat, because no matter how we number, we're going to go 1, and then the lowest number is 3. If we start on orange or yellow, they're always going to be numbered 1, then 2, right? So the orange one will be 1, then the methyl group's 2, or yellow, methyl group's 1, ethyl group's 2. So we know we're not going to start at the blue carbon because we have 2 groups that are side by side. So if we start at, the yellow carbon, and that's 1, 2, and then that puts this group at 4. If we start at the orange carbon, we get 1, 2, 3, 4, 5, 6. So we're going to start numbering at the yellow carbon. Everyone see that? That makes sense? So this will be, try not to mess it up, ethyl, methyl, propyl. It's going to be 1, 2, 4. Oakley Doakley?
I was asked why the first substituent doesn't get number 1 in the name.
Which one is the first substituent? Oh, no. So you're still going to try to put the lowest possible number in your name, but that has to be now the second substituent. And here it's 1, 2, 1, 2, and now that's tied. So now you look to give the lowest possible number to the substituent after that. Yeah, so wherever you start is going to be 1, and in this case you're going to have 2, and then you go to the next one. Yeah, so wherever we start is kind of our first substituent. All right. So show this real quick. Kind of goes to numbering, so all right, so let's say we have something like this. What's the parent hydrocarbon?
The response was heptane.
Ah, you fell into the trap. Thank you. So, this carbon right here always belongs to the ring. We don't get to count it as belonging to another chain. It's just, I have 2 propyl groups, but this carbon doesn't get to belong to a heptane chain because it already belongs to the ring. So you don't get to count through one of the carbons on the ring to make a longer chain. That carbon, this green carbon, belongs to the ring and doesn't get to belong to any chains. So this would be dipropyl cyclopentane. And here we have, now I have two groups, so I have to have numbers, even though the numbers are going to be 1, 1. So even though it's 1, 1 dipropyl, you have to put both numbers, because if you just don't put any numbers, you don't know where those groups are relative to each other. It could be 1, 2, 1, 3. You have to make sure you put numbers as soon as you get above one substituent. So what's my parent hydrocarbon here? I think it's octane. 1, 2, 3, 4, 5, 6, 7, 8. So cyclooctane, we'll get this a little closer together. What are my substituents? It is. So we've got ethyl dimethyl cyclooctane. Now do I start numbering at the orange carbon, or do I start numbering at the blue carbon? Orange. So the reason is, either way I number, I'm going to start with number 1. But if I start at the orange carbon, I get 1, and then what's my second number in my name? I get another 1. I'm 1, 1, then I'm 3. If I start at the blue carbon, I'm 1, then I'm 3, 3. So my second number is 3. So I'm going to start at the orange carbon, so I get 1, 1. So I have 3-ethyl 1, 1 dimethyl cyclooctane. All right, so parent hydrocarbon here. Just kind of giving it away, give away the game. Cyclohexane, right? I have a methyl and an ethyl. Right? And now, cyclo as a prefix isn't telling me a number, it's telling me the structure of the substituent. So that C in cyclo counts alphabetically for where we're going to put cyclopropane or cyclopropyl in our name. So it's going to come before ethyl. So it's going to be cyclopropyl, like we're going to pretend it all fit. And like we're going to have space for that number. Cyclopropyl, ethyl, methyl, cyclohexane. So now, same thing. I'm going to start numbering at the orange carbon because that gives me 2 1s in my name. So I'm going to get 1 methyl, 1 ethyl, 4. So 1, 2, 3, 4. 4 cyclopropyl, 1 ethyl, 1 methyl, cyclohexane.
I got asked if we could start at the blue carbon, the one with the cyclopropyl, as our numbering, so we would start there with a 1.
No, because think about your first number in your name is 1. and then you want to make the next number in your name as small as possible. If you do 1 and then 4, right, that is, 4 is going to be greater than having 1 and then 1. So far, so good? All right. So this is a question that came up in the early class. I'll address it now. Someone asked, what if you have two rings that are the same size? Right? I'll make this ring A, this ring B. Right? Which one do you pick as your parent hydrocarbon? And I said you're going to pick the one that has the most substituents as your parent hydrocarbon. So here, like ring B has 2 groups coming off of it. Ring A has 1. So it's easier to name this molecule if you pick ring B as your parent hydrocarbon. So this would be like cyclohexyl methyl cyclohexane. So we're using ring B as the parent hydrocarbon because it has 2 groups coming off of it. So this is going to be then 1 and 3. I am pretty sure I'm not going to get that tricky. Ain't nobody got time for that. But there you go. So we feel solid about basic nomenclature stuff. Rings are pretty much just like everything else. So are we good? All right, cool. So the last thing I want to go over today is types of carbons. It's kind of naming, kind of categorization. Right? So being able to categorize carbons is important because different carbons react differently. And where a chain is bonded changes the name, right? We've already seen this, right? So 4 carbons in a straight line, 1, 2, 3, 4. That group is butyl, right? But if I have 4 carbons where the R group is off the second carbon, right? That is sec butyl. So, just being able to identify different carbons and classify them also is important for naming, right? So there are 4 types of carbons, right? The first type is primary, or R primary. So that's just, primary is a carbon bonded to one other carbon. So when I'm saying bonded, I'm meaning directly bonded. So this carbon right here is directly bonded to one other carbon. So this carbon is a primary carbon. This carbon is a primary carbon because they're bonded to one other carbon. If I had this, and this, these are all primary carbons because they're all directly bonded to one other carbon.
Handwriting is trash, and someone thought that my one with a superscript circle was just a 10.
Sorry. It's like 1 and then like a degree sign. Sure. Again. the handwriting's not great to begin with, and like I ordered a finer tip stylus that'll hopefully come Sunday. So they say a good craftsman doesn't blame his tools, but I'm not a good craftsman, so we're gonna blame my stylus. We'll see if a new stylus helps. All right, so we have secondary. See if I can do this where it doesn't look like a 20 this time. Little degree sign, carbon, bonded to 2 carbons. So here, here, and here, each of these carbons is bonded to 2 other carbons. So those carbons are secondary. So this is where the sec in sec-butyl comes from, right? Because our R group comes off of a secondary carbon. So the sec in sec-butyl, the sec is indicating that you're bonded to the secondary carbon, that your longer chain is bonded to the secondary carbon, not the primary carbon. We have tertiary. This is a carbon that's bonded to 3 carbons. So this carbon right here is tertiary. It's bonded to 3 other carbons, right? 1, 2, 3. This carbon and this carbon are both tertiary. And then we have the last one here, which is quaternary. I can draw a circle, I promise. This is a carbon bonded to 4 carbons. So this is going to be something like, this carbon is quaternary. So then these 2 carbons here are quaternary. Easy enough? Yes, if you can count to 4, you're golden. What type of carbon is that? Tertiary. What about that? Quaternary. That one? The blue one? Secondary. bonded to two different things. What about the green end? That was tertiary. We'll pick another color here. What about that orange one? Primary. So it's super straightforward. So this is going to be really important later on when we start doing some reactivity where certain reactions can happen at a primary carbon but not a tertiary carbon, or they happen at tertiary carbons and not primary carbons. So being able to quickly classify your carbons just by looking at a structure will let you know what reactions can and can't occur at that carbon. So I think that is probably the lecture for today.